Hello, in this video we'll continue with our treatment of predicate logic semantics. In our previous lesson we went through some examples of interpretation in PL. Now it's time to take a more rigorous approach. To do so, we're going to start by providing a definition of an interpretation. A predicate logic interpretation consists of a non-empty collection of objects, called the domain, a name for each object in the domain, and remember that a given object may have more than one name, but that names can't be ambiguous and no object can remain nameless. An interpretation also implicitly contains a list of predicates. And last, a specification of the objects of which each predicate is true, and those of which each predicate is false. Just like we can talk about the interpretation of a whole language or a whole language fragment, we can also work with the smallest case, the interpretation of a single sentence. Of course, this is only a special case of the notion of an interpretation for a set of sentences. That is, the case in which the set is one-membered. An interpretation of a sentence X is an interpretation that contains enough information to determine whether X is true or false. Such interpretation includes all the names and predicates occurring in X, as well as the truth values for all the atomic sentences in X. For example, let's give an interpretation for the sentence WH and SGG. To do so, we need to specify a domain, which, if you remember, amounts to a list of the names of the objects in the domain, and truth values of all the atomic sentences you can form with the names and predicates in the interpretation. Let's get started. The domain must contain all the names that appear in our sentence. In this case, they are G and H. We could include more names if we wanted, but there would be no use in that. Implicitly, our list of predicates contains all the predicates that appear in our sentence. In this case, they are the one-place predicate W and the two-place relation S. In your mind, if that helps you, you can associate these PL predicates with English ones, such as waits or sees. Now we have to provide values for all the possible atomic sentences that can be formed by crossing our list of names with our list of predicates. Let's start with W. This is a one-place predicate, and given that we only have two names, only two atomic sentences can be formed here, WG and WH. This could be Gabe waits and Heather waits, respectively. Now, let's do the dyadic relation S. How many atomic sentences do we get when we feed our two names into this relation? This predicate has two places. There are two candidates for filling the first gap, G and H. Likewise, G and H are the candidates for filling the second gap. So we have a total of 4 sentences, the result of multiplying 2 times 2. The first one results by putting G in both the first and second gaps, and is SGG. Read it as Gabe sees Gabe, or Gabe sees himself. In the second one, G occupies the first place and H the second, so you get SGH, Gabe sees Heather. And so on for the other two. So we have 2 plus 4, that is 6 atomic sentences in total. If you're wondering why we're bothering with all these extra sentences, well, this is because all these other formulas are going to be needed when we deal with quantified sentences. Now back to our interpretation. Which values should we give to all these sentences? Well, whichever you want, as long as all the atomic sentences have one and only one value. So we could give T's to both WH and SGG, and then give random values to all the other sentences. This is an interpretation for WH and SGG since, given all this setup, this sentence is endowed with the truth value. It is also a model for the sentence, since it comes out true in this interpretation, as you can easily see. But suppose we assign T to WH and F to SGG, and again, more or less randomly fill the other cells. Then, this is certainly an interpretation for WH and SGG, but not a model for it, since it comes out false here. Now, suppose that we toss out the name H and only keep G. Then, the only 2 atomic sentences we can form with our 2 predicates and our single name are WG and SGG. Just for giggles, let's make both of them true. It doesn't matter, really. Then we have a value for SGG, but not for WH, since it doesn't show up in our list. Therefore, we can't calculate the truth value for a target sentence. So this is not an interpretation for WH and SGG, since it doesn't contain enough information to determine whether it's true or false. Let's do another example, this time a quantified sentence. Again, let's do this intuitively. This says that every X stands in the relation L to A. Imagine that this is everybody loves Al. Let's add two names in the domain, A and B, or Al and Beth. This results in 4 atomic sentences, to which we assign these values. Now, is it true that everybody loves Al? These are the 2 relevant sentences. It turns out that Al doesn't love himself, and that Beth doesn't love Al either. So the sentence, everybody loves Al, is interpreted as false here. As a matter of fact, 2 names are unnecessary. We could make do with only 1 name, which is the minimum. And the name we have to choose is A, since it already shows up in the formula. So we are imagining a universe in which only Al exists. So the only question is, does Al love himself? Let's not be cruel. Let's say that he does love himself. In this case, everybody loves Al is true, since Al is the only member of the domain. And all of this leads us straightforwardly to the notion of truth in an interpretation. In predicate logic, we never say that a sentence is true or false, period. Rather, what we say is that a sentence is true or false at a given interpretation. So we can take our first steps towards providing a broad enough definition of truth in an interpretation that will accommodate quantified sentences along non-quantified ones. Regrettably, these initial steps will have to remain rather informal and inadequate, since this is not general enough to cover cases with multiple quantifiers. But as they say, it's better to proceed slowly but steadily, and next week we'll tell the complete story, or at least a more complete story. In any case, here it goes. Let's say that a universally quantified sentence is true in an interpretation G if, in G, it is true for everything to which the variable could refer. That is to say, it is true of every value of the variable. Correspondingly, an existentially quantified sentence is true in an interpretation G if, in G, it is true for at least one thing to which the variable could refer. So, it is true for some value of the variable. But then, what is it for a sentence to be true for or true of a value of a variable? This can be expressed in terms of substitution instances for quantified formulae. There are other methods, but this is the one that we'll follow here. To explain this notion, we need to make a brief parenthesis in our semantic discussion and talk a little bit more syntax. Again, at this point, we can only give a provisional definition of substitution instance, a definition that will only apply to cases in which we have only one quantifier. Okay, here it goes. For a universally quantified sentence of this form, and here U can be any variable, x, y, z, any variable, what this is telling us is that there is one quantifier, and that the occurrences of variables in the quantifier scope are bound by this quantifier. Okay, for a universally quantified sentence, a substitution instance with the name S substituted for U is the sentence formed by first dropping the initial quantifier and then writing S whenever U had occurred. Here's an example. Suppose that we have the sentence every X are X, and the domain contains 3 names, A, B, and C. How do we get substitution instances for this sentence? Well, a substitution instance with the name A substituted for X is the sentence formed by dropping the initial universal quantifier and then writing A wherever X had occurred. So, one substitution instance is this, RA. Notice that the quantifier is gone and that the variable has been substituted by the name A. Likewise, this would be another substitution instance, this time with B. And we can do the same with C. So we have 3 substitution instances for every X are X, namely RA, RB, and RC. Remember that when we substitute a name for a variable, we have to write the name in all the places where that variable was bound by the quantifier. Here we have the sentence every X, LXX. So we'll replace A for the first occurrence of X, but we're not done yet. The other occurrence of X also needs to be replaced to yield LAA. So we have LAA as a substitution instance of every X, LXX, but we also have 2 other names, B and C. So LBB is another instance, and so is LCC. So these are the three substitution instances of every x, LXX, using the names A, B, and C. The same procedure applies for existential sentences. Let's get all the substitution instances for some y, HBY, using the names A, B, and C. Here, even though the predicate has two places, only one of them is occupied by a variable. The name B is permanent and can't be changed. Think of this sentence as, there is someone whom Beth hates. And so think of the predicate not as the naked two-place relation X hates Y, but as the predicate Beth hates Y. Okay? So the substitution instances are obtained by deleting the backwards E and substituting the occurrence of Y with a name. Like this, with A. This instance would be Beth hates Al. And now with the next name in the list. Beth hates herself. Well, it figures. Last, we use C, Beth hates Claire. So these are the three substitution instances of there is a Y such that H be Y, using these names. So now that we have mastered the notion of substitution instance, we can use it to calculate the truth values of quantified sentences with respect to specific interpretations. Let's start with this sentence. Every x stands in the relation L to A. Remember that we could think of this as everybody loves Al. Let's use interpretation G with two objects in the domain, called A and B. Since we have a two-place predicate and two objects, then the number of atomic sentences is 4. And for no reason at all, I've given them these values. Okay, now let's proceed methodically to evaluate our target sentence. Remember that a universally quantified sentence is true at an interpretation G if all of its substitution instances are true in G. And what are the substitution instances of every x LXA here? LAA and LBA. If we consult our table, we see that LAA is true, but LBA is false. Hence, not all the substitution instances of every x LXA are true in G. And so, every x LXA is false in interpretation G. But what happens if we swap our universal quantifier for an existential one in the same sentence? The substitution instances are exactly the same, LAA, which is true, and LBA, which is false. But then, an existentially quantified sentence is true at an interpretation G if and only if at least one of its substitution instances is true in G. And this is precisely the case, since LAA is a substitution instance and it's true. So there is an x LXA is true in G. Okay, this is all for this video. Goodbye.